Wouldn't it be great if there was a piece of software that you could give your simulation to, and it would just tell you how many replications you need to run of it? Well, it turns out that hidden away behind a journal paywall is an answer to that question. Hoad and colleagues developed an automated approach to selecting the number of replications. They developed this approach for non-specialists to provide guidance on the number of replications required. What's cool about this approach is they found that it's consistent in selecting the expected number of replications required for a model output. So that's really exciting for us, particularly within a digital twin context where we heavily rely on the quality of automated decisions. So in this video, we're going to unpack that algorithm and we're going to implement it in Python. And by the end of this video, you're going to have a framework for the replications algorithm that you can use with any Python simulation model. If you do use the code that we develop in this video, perhaps you could click the like button and subscribe to the channel. I'd also ask you to cite this journal article itself as a nice thank you to the authors that developed this work. Let's take a look at the framework we're going to set up to allow us to run the replications algorithm. We're going to work towards coding a replications algorithm class. That's going to accept a number of optional parameters that will allow us to control how the algorithm behaves and the results it returns. We're going to make use of a design pattern from object-oriented programming called the adapter pattern. That's going to allow us to adapt any Python simulation model to run with our algorithm without needing to adapt the code. So our models are going to be instances of a replications algorithm model adapter. And to run the algorithm, it will be as simple as calling the select method. And we'll pass in our adapted simulation model. We'll run that and we'll obtain a number of replications that we need to run for that model. The simulation model we're going to use in this video is one I've developed, and it's called TreatSim, and it can be installed from PyPy. We don't need to know too much about the specifics of TreatSim, but it contains a number of queues within an emergency department type setting, and it's going to give us lots of performance measures that we can explore in a replication analysis. To run a replication of the model, we first need to create an instance of scenario. That could be a default scenario, or we could vary the parameters of the model and create a different scenario. We take that scenario and we pass it to the single run function. Single run is going to return results from one replication of the model with a given set of random numbers. Let's take a look at the results. So here's a single replication of the model, and we can see we've got a lot of performance measures that have come out of the model. Different types of waiting time and utilization of resources. That's a repeatable result, so each time we run that single run function with random number set 1, we obtain the same results. If I vary that number, for example to number 2, I get a different set of results. So TreatSim is set up in a way where you can sequentially run replications of the model. You're going to see that's going to come in useful later on. The replication algorithm builds on a classical output analysis approach. It's called the confidence interval method. Rather than spending time looking at the formula for how this works, I thought it might make sense to look at some code and also a visual representation of what's going on. And I'm also going to show you one of the flaws of the confidence interval method with our first example. I'm going to start by running 150 multiple replications of our model. That's going to return a pandas data frame called replication results. Each row is a replication of the model, and each column is one of the performance measures from that run. I'm going to pass the replication results, and in particular one of the performance measures, waiting time for trauma treatment, to the confidence interval method function. That's going to return the number of replications it recommends and a data frame of the confidence interval method results. I'm going to set this mysterious parameter as well, the desired precision, set that to 0.1. More about what that means in a moment. Here is our first problem with the confidence interval method. The replications do not reach the desired precision. So we've not run enough replications of our model. So here's our first problem with including the confidence interval method in an automated pipeline of some description. We don't know how many replications we need to run in order to achieve this mysterious required precision of our model. Let's have a look what's been returned. So it's been unable to return the number of replications. It's returned -1. And let's have a look at this confidence interval table. I'll pass that to one of my custom functions called plotly confidence interval. That returns an interactive plot, and what it's showing here is the cumulative mean of the treatment waiting times for trauma patients. That's in dark blue, this dark blue line, and we can see that that's a bit wobbly to start off with, and it starts to stabilize the more replications we run, which is our x-axis. Those lighter blue dashed lines are the upper and lower 95% confidence interval. So if we go to 100 replications, we can see that the lower interval was 14.93 and the upper was 20.96. So they're symmetrical about that cumulative mean of around 18. The deviation of the half width of that interval from the mean is around 17% at 100 replications. So that's talking about the distance from here up to here divided by the mean. So that's the half width of the interval divided by the mean. And that's our precision. The confidence interval method aims to get that precision below some target value that you've specified, and it hopes that that's an idea of stability of the estimate of the mean. So you can see here at lower replications, we're quite unsure, actually, have we got a stable estimate of the mean? Whereas when we get up to higher numbers, we're starting to get an idea that we do have a stable mean, although it's not falling below our requirement of 10% that we set in this case. Let's repeat that for a second performance measure. This time we'll look at waiting times for triage within TreatSim, and I'm going to again set my desired precision to 0.1. We'll print out the number of replications it's returned, and we'll show the plotly confidence interval method. So in this case, it's been successful, and it's highlighted that at 145 replications, the waiting time for triage, the precision has stabilized below 10%. So if we go back one replication to 144, we can see it's just over 10%. And then we can go a bit further on and check, is that stable? It's still below 10%, it's still below 10%, it's still below 10%, etc. Okay, so that would be a good estimate of the number of replications that we need to run in this case. So underneath that plotly chart is a simple table where we can see the mean of each replication. We can see what that means in terms of the cumulative mean, which is these two, in for the second row, which is the mean of these two values. And then we can start looking at the standard deviation and the upper and lower confidence interval of that cumulative mean as well, and what the half-width percentage deviation is. So a big flaw of that approach is that we can't include it in an automated pipeline because we don't know how many replications we should run in advance in order to check we've got enough. So we risk underrunning and we also risk overrunning. And there's also a risk that even when we hit our percentage deviation, if we run a few more replications, we might find that it increases above that percentage deviation again. And so we wouldn't have a stable estimate of the mean. So the replications algorithm extends that confidence interval approach into what we would call a sequential algorithm. What that means is we're going to perform single runs of our model, individual replications, make some decisions and decide if we continue running the model for longer or if we return a result. The second thing that the replication algorithm introduces is a look-ahead period. The way this works is that once the desired precision of the half-width has been encountered, the algorithm will enter a second loop and look ahead for k periods to check, basically, if that precision continues. If it doesn't continue, then we need to run more replications of the model. So what we're going to do is provide information on the look-ahead period. We're going to add information on our desired precision. In our case, we're going to go for the default of 10% of the mean. We're going to provide the significance level, alpha. That's going to decide if we use, for example, a 95% confidence interval or a 90% confidence interval. And we're going to set up the single performance measure version of the model. So we'll provide a name of a performance measure that we're going to use. To start off with, the algorithm simulates an initial number of replications. Typically, that would be 3 replications. That's what the authors recommend. We're also going to track a value called converged. We'll set that initially to false. And each time we hit the desired precision, we'll flip that over to true, and then we'll run a look-ahead period to check, are we maintaining that convergence? So it all takes place in a big while loop. Effectively, while converged equals false, we're going to run this code. The first thing we do is we calculate our cumulative mean, which I'm calling xn here, and check what precision has been achieved after those n replications. We'll make a decision here about have we achieved that or not. If no, which is pretty likely to start off with, we'll increase the number of replications we're going to run and run that extra replication. And we'll go round in this loop until we hit this condition where our current precision is equal to or less than our required precision of 10%. We'll then enter this second loop. So at this point, we've potentially converged on the number of replications we need to run. So we set that to true, and we store the solution value, the number of replications we need to run, in a variable called nsol. We're then going to run a look-ahead period using the value k, and that's going to go up to replication n plus k limit. More on this value in a moment. So first of all, we run replication n plus k. We update xn and dn at each iteration. We check if the new precision is now breaching our required precision. If it has, we terminate this loop and we go back up and run more replication of our model until we hit that precision again. If everything's still okay, we increase k by 1. We check to see, have we hit k limit? Have we run the full lookup period? If not, we carry on and we go round in this loop until we've run the full lookup period, and then we return nsol to the user. So how does k limit work? Well, the first thing to say is that Hoad and colleagues recommend a lookup value of 5 based on their extensive empirical work. But it's a bit more complicated than that, and it's dictated by this formula here. Now, don't let this scare you. It's actually really quite simple. If the number of replications is greater than or equal to 100, then a fraction is calculated. And that fraction is k limit divided by 100 multiplied by the number of replications. And these symbols, these strange brackets here on the side of the function, just means that it has to return an integer value. So to give you an idea of what's going on, if we have a k limit of 5 and we're running 50 replications, that means you would simulate an extra 5 replications in your lookup period. If you were up to 800 replication and you'd set your initial k limit to 5, that means you would simulate 5 divided by 100 times 800 equals 40 replications of the model. So I think that's quite enough of the theory of the replication algorithm. Let's go ahead and implement that in Python and then have a go at it. That's what we want to get to. So I've provided some classes in a utility module called Reputility for you that are going to help us do that in an efficient and useful way. The first of those is online statistics. That's going to implement Welford's method for computing online means and variance. What that means in English is it's an efficient way of calculating the running mean and the running variance as we add more replications to it. I've also provided Replication Tabulizer and Observer, and they're going to help us with looking at the results at the end. For example, if we wanted to look at a Plotly chart of the confidence intervals. Let's have a go with online statistics first. So the replication algorithm recommends we run 3 initial replications. We'll do that. I'm going to create an instance of Replication Tabulizer. I'm going to call that Observer, and that's just going to observe the online statistics as we compute more replications and store the results in a table for us to look at the end. That's an optional parameter to online statistics. We'll also pass in an optional parameter of the initial results. Then we'll print out the current cumulative mean and the current deviation. Now, sequentially means that we can add more data to those online statistics as we go along. So here we'll perform a single run of the TreatSim model, and we're going to use random number set 3 as it's the 3rd replication, and we're going to store the results for the triage waiting time. We're going to put that in a value called xi just to show you that's just a simple result from the replication. Then we're going to call the statistics update method, pass in that new result, and we get the update to the cumulative mean and the current deviation. You can see that's nowhere near what we need it to be. And you would just keep repeating that. So we would run another single run of the model. We would use a different random number set equal to the replication number. We would update statistics and have a look at the cumulative mean and the deviation. If we do that long enough, we can use the observer object to just present that as a confidence interval table. So we've got the mean of the replications. So these are the first 3 that we ran. We've got the cumulative mean up to that point. We've got the standard deviation, the upper and lower confidence interval, and the current percentage deviation, our precision that has been achieved. Let's take a look at our first iteration of the algorithms class. These are the optional parameters we can include. We can include a parameter that varies if this is a 95% confidence interval or a 90% confidence interval. We can specify our half-width precision, our percentage deviation. In this case, it defaults to 0.1, but you could, for example, try and run that for 0.05. Just note, if you do that, you're going to require a lot more replication to achieve that precision. We can specify the initial number of replications we run. That's going to be set to 3 by default, which is the recommended number from Hoad and colleagues. We'll specify a lookup period. That's going to be 5 by default, again a recommended number from Hoad and colleagues. Our next parameter is called replication budget. So this is a fail-safe mechanism I've built into the class. It's a hard limit on the number of replications I will allow this to run for. Now, if you have a digital twin where each replication is quite slow, there may be a computational budget, a time limit on which you can run this analysis for. So replication budget can be used to limit the analysis if it does look like there is a problem. Nothing complicated going on in the initializer of the class. We're just storing all of the values that we've passed in. One thing to point out is we track the current replication number in a member attribute called n, and we have n solution, which is the solution we will return to the user at the end. And we'll set that to our fail-safe option of replication budget to begin with. Next up is the k-limit method. That's going to look at the current replication number and decide, are we returning the user-specified look-ahead period, or are we going to return a fraction of the current number of replications that we've run? So finally, we get to the meat of the algorithm with the select method. That's going to return an integer value, which is our solution, the number of replications to run. We'll pass in an instance of scenario for TreatSim, and we'll pass in a string, which is the metric we're interested in. So this code just implements the process flowchart that I described earlier. We have some initial operations that we complete, such as running an initial 3 replications of the model. And then there's 2 loops. There's an outer loop where we're going to loop until we've converged or until we've run out of simulation budget. that's going to sequentially update the cumulative mean, the confidence intervals, and the current precision until we hit this if statement here where our target precision is met. Once that's happened, we've potentially converged and found our solution. So we remember the number of replications that we've run up to this point. And then depending on the value of k-limit that we've set, and remember the default is 5, we then have an inner loop, and that's going to loop for k-limit additional replications. So all that does is run another replication of the model, update the statistics, and just check what's happened. Are we still within the deviation we expected, or has the deviation increased again? If it has, then we're going to break out of that loop and start more sequential replications from where we've got to. Otherwise, we increase k and we go back round that loop again. Once we break out of that, we check, have we converged? If so, then we return our solution to our user. Now, because we've included a failsafe, we need a bit of code here to deal with that. So if we don't converge and we break out of that outer while loop, we need to warn the user that we've not converged, and that's what we're doing here with the warnings package. And we return the solution, which will be the maximum number of replications that we've allowed. So let's see that running. Just to remember, these are all of the performance measures we can select from TreatSim. I'm going to use the wait for trauma patients for cubicle treatment because we didn't manage to run enough replications earlier when we used the standard confidence interval method. So we're going to create an instance of replication tabulizer so we can have a look at this in Plotly afterwards. Then create an instance of our replications algorithm and pass in that observer object and set verbose to false. We then call analyzer.select, pass in our scenario and the metric that we're interested in, and that returns our number of replications, and we'll print that out to the screen. So it's selected 219 replications in order to hit a mean deviation of 0.1 or 10%. So if we want to, we can have a look at the summary table that the observer put together for us. That's just a standard confidence interval method table. So that means we can then pass that to the Plotly confidence interval method and have a look at it graphically. So we can see here that as we approach 219, we're above 10% deviation and we very, very slowly converge. Right there on 218, we're just above 10% deviation from the mean. Then we go just below it at 219. And if we go through the look ahead period, we can see that we stay below it. So if we wanted to, we could change the metric we're going to run through the replications analyzer. So we could have a look at waiting for triage, which came back from the confidence interval method with 145. Let's try that here. Yep, and it's come out with what we've expected. Now, what we could do is aim for an even more precise confidence interval around our mean, but if we wanted to, we could change the half-width precision parameter. And gosh, we need an awful lot more replication in order to achieve that. And you have to wonder if that would be worth it in this case. So if we have a look at the code again, in order to run a single replication of the model, we call the single run function of TreatSim. We pass in the scenario and the random number set. That returns a pandas data frame, so we need to use the iloc accessor and specify an element of that we are interested in looking at. So that's specific to TreatSim. So if you wanted to run this with your own code, you would need to modify this line of code, and probably you'd need to modify the method signature as well, as you might not have a scenario class. It might be set up slightly differently. So as a software engineer, I would say that's a poor way to design your code. So instead of that, what we'll do is think about object-oriented design, and we'll implement the adapter pattern, which is the open-closed principle, where our main class is closed to modification, but open to extension. So what we'll do is we'll make a protocol class And we'll call that the Replications Algorithm Model Adapter. A bit of a mouthful, but it will be an interface that all models that use the replication algorithm have to abide to. That's going to have a single function, and it's called single run. All that requires is an integer value which represents the replication number, and it will return a float which will be a quantitative value from the simulation. So it inherits from the protocol class, which means that we can formalize Python's duck typing and make sure that any class that we pass into Replications Analyzer adheres to this interface. So here's our treatsim adapter. So this is a bit like fitting a square peg into a round hole. How can we do that? Well, we can create a class that wraps around our current simulation model and changes its interface. So when we create an instance of treatsim adapter, we're going to pass in our scenario, the metric we're interested in, but we're also going to pass in our single run function. We're going to pass in the actual function that runs the model. In this case, we're also going to pass in the run length in case we want to change that. And we store all of that within the initializer method. And then when we implement the interface from our protocol, we create a function called single run, give it the same method signature as our protocol. So it accepts an integer and returns a float. And then within that, we call our single run function, pass in our scenario, pass in our run length, and pass in our replication number. And we can manipulate the data however we want to return a float value. So in this case, because treatsim returns a data frame, we use ilock. So now we create an instance of treatsim adapter. We pass in our scenario, our metric, and our single run function, and then we have an object of type treatsim adapter that implements our adapter protocol, and we call the single run method and pass in the replication number, and we get a return value which is the mean of replication 1 for triage waiting time. Now we also made our protocol runtime checkable. So if we wanted to, we can validate the interface of any models that are passed into Replication Analyzer. So we use the isInstance function there. We pass in our object and we pass in the class that we want to check it's of a type of. So we can see here that Python recognizes that our TS model object adheres to the adapter protocol that we put together. So that means we can create a modified version of the replications algorithm that can handle any model as long as we've set up an adapter for that model to work with our adapter protocol. But our method signature of our select function looks slightly different. So rather than passing in the scenario and the metric, now we pass in an instance of a replications algorithm model adapter, our protocol, our interface. Okay, and we can have a bit of validation here to just check that the model adheres to that interface. If not, we can raise a value error and stop this from ever being run in the first place. And then the code looks the same apart from each time we run a replication of the model. We use the single run function of the model that's been passed in, pass in the replication, and hey presto, we've uncoupled our model from our replication algorithm. So replication algorithm is closed to modification, but it's open to extension. We can extend it to work with any model. Okay, so now when we want to run our model, we create an instance of scenario, we create an instance of our treatsim adapter, pass in the scenario and the metric and the single run function. Then we run our algorithm and our select method takes an instance of our treatsim adapter. So there we go, we've got our 145 replications, same as we did before. So if you've managed to make it this far into the video, well done. As an extra bonus, what I'm going to tell you is that you could simply pip install my package SimTools and you would have access to the replication algorithm. You can also install that from Conda Forge using Mamba or Conda. So in order to use that, we import replication algorithm from SimTools output analysis module. And then we would need to create an adapter just as we did before. So in this case, we've got the treat_sim adapter. We would pass that to the replication algorithm select method, and we would obtain the number of replications that we need to run. I'll link to the GitHub repo containing all of the code we've been through today in the description below. There's some bonus code in the notebook if you wanted to take a look, which adapts a call center simulation to run with the replications algorithm as well. I'll see you in the next video.